Yeah.
Greetings and welcome, friends. We're taking a look at last night's quest on page 554 about graphing rational functions. Problem 17 specifically said, state the equations of the vertical and the horizontal asymptotes for each rational equation. Now, I might even do you one better than that. We'll see. Oh, I don't want to scroll down too far. It's kind of revealing my hand there. So let's see. H of x equals x minus 1 over x minus 3. Now, I might actually go beyond what they were asking. We might actually even talk a little bit about domain and range rather than just the asymptotes, just so that we gain from this learning experience. Now, regarding the domain, we can determine what doesn't work by figuring out when is the denominator equal to 0. So I'm going to say x minus 3, you cannot equal 0. Never. Right? And then I solve that not equation, and I get x is not equal to 3. All right, so my domain is actually going to be the set of all real numbers, set of all x, such that x is not equal to 3. In this case, that is also kind of telling me where my vertical asymptote is. All right, in this case, where I know x equals 3 is going to be a vertical asymptote. Now, to determine horizontal asymptotes, that was all about the end behavior of this graph. And I taught you a trick where it's all about comparing the ratio of the leading terms. All right? So for the leading terms, I have x to the first over x to the first. Now, when it's a tie between their degrees, you actually figure out what the ratio is of their coefficients. So 1 over 1 is 1. So therefore, my horizontal asymptote is 1 over 1, or 1. And typically, in some of our graphs, that also would reflect what the range is. The range could be everything but 1. That's not always the case. So this I'd say always be careful of and kind of check by analyzing your asymptotes of the rest of your graph and blah, blah, blah. Yeah, in some cases. That's where also we can pull in a table, but we'll be doing that in the next two problems. So that's where those asymptotes would be. To verify, let's graph this real quick. Let's see, what was that equation? It was x minus 1 over x minus 3. So I'm going to have to parenthesize both the numerator and the denominator. And behold, this is my graph right there. What do you know? What do you know? So you can see that there is a vertical asymptote at 3, and you can see that there's a horizontal asymptote at 1. Now think about really, really big values of x, all right? Like if I'm thinking like a billion, plugging in a billion. Now if I'm comparing a billion minus 1 to a billion minus 3, that's kind of like just 1, right? Like, yeah, it's like billion over a billion kind of sort of simplifies to 1-ish. And that's what we're seeing. The bigger the values are, the less influence this minus 1 and this minus 3 have. They're kind of like, let's not even fight anymore. We're all super filthy rich, right? And then similarly for negative big numbers, if I plug in negative billion, a negative billion in 1 divided by a negative billion in 3, right? The minus signs cancel out. That's why it's positive over here, positive 1-ish, because the billion in 1 and the billion in 3 are kind of same-ish, so they're just getting closer and closer to 1 the bigger the numbers I plug in. And that's the idea behind these asymptotes existing. So let's look at the next question. Here we've got problem 19. In this case, they actually asked us to graph this, so we're going to analyze it on all levels. So I'm going to be interested in the domain, the range, and the asymptotes. And I'm also going to end up making my little table of values here in a moment. So the domain, what x value does not work? 0. That denominator cannot equal 0. That's two things that won't work. Classic Sponge. That's my favorite SpongeBob quote of all time, by the way. Now, checking out the asymptote, that means x equals 0 is likely also going to be vertical asymptote. For my horizontal asymptote, look at my leading terms. This is 3 over x you could view this as x to the 0 and x to the first. So which one wins? The denominator. So if I'm in a race to infinity, all right, which is getting to infinity faster? Is 3 or x getting closer to infinity as I plug in really big numbers? X is getting really big and 3 is smaller, right? So what happens is, if I take 3 and divide by a really big number, my result is going to be really small. So it turns out that for extreme values that this is going to be approaching 0. It's getting smaller and smaller as time goes on. And for positive values of x, a positive divided by a positive is positive, so it would be approaching 0 from the top. For negative values of x, a positive divided by a negative is negative, and it would be approaching 0 from the bottom, right? And now I suspect also in this case that my range is the set of all y such that y cannot equal 0. So it turns out this 3 actually didn't have too much influence on it, as like it could have been a 1 or a 7 or a 300. Those graphs aren't significantly different in general shape. Let's take a look at the chart. Look at the chart. Here we are. So I'm going to edit my chart here. So I need to rewrite this as 3 divided by x, and my x is the third cell here, A3. Hit enter. And then I get my little black plus sign and drag it down. And there we go. It's plugged in all those values. I think I can change my center to focusing on 0. And let's take a little snapshot of this and analyze my input-output table, friends. So I'm just going to paste that right over that. Bam. There we go. I don't even care. So let's analyze. Notice I do have an undefined point, divide by 0 error at x equals 0, which is what we were describing. It is asymptotic. This is approaching positive infinity, and this is approaching negative infinity, right? And then for really extreme values of x, Gimondo ones, notice this is getting smaller and smaller and smaller. It's actually approaching 0 from the positive side, and this is getting smaller and smaller and smaller. This is approaching 0 from the negative side. So combining those things, if I wanted to, I don't know, say graph this, let me just, bam, delete that and hide some of these. Hide them. Bam. I'll take a little snapshot of this, and we'll make our own graph, and then we'll compare it to the computer-generated graph. Right, Jacob and Hank? That's right, friends. So let's draw our asymptote. We have the vertical one. We've got the horizontal one. And then based on my analysis, actually I might even use purple for this, why not? Of this, I know it's approaching 0 from the negative side over here. So I know it's like this. I know it's approaching negative infinity there. I know it's approaching 0 from the positive side there. And it's approaching infinity over there. So I could draw this technically if I wanted. What an ugly graph I've drawn. If I wanted, I could actually look at some of my points from my table. For instance, I could have realized at 3 it crossed through 1 here. So I might have then realized I have to pull that down a little bit more. But that's fine. I'm looking for just the general shape. So if I graph, what was this, 3 over x? Notice, let's even scroll down right there and line it up. Oh, look at that. Thing of beauty. Look at that. Oh, yep, That's pretty good. I'm happy with that. Are you guys? Yeah, look at that. That's not bad at all. So we got the general idea. We've got the right portions of this drawn. We've got the asymptotes in the right place. We're looking good. Let's look at this last question. What was this? 25. That's right. Now this one actually has some interesting behavior where I've got f of x equals x squared minus 36 all over x plus 6. Now what's interesting about this is the numerator is factorable, okay? So I am able to actually rewrite that. That's a difference of squares pattern. That's the same as x plus 6 times x minus 6, right? Sum and difference pattern over x plus 6. So if I was to kind of simplify this-ish, I could kind of cancel that out, and I would end up getting just x minus 6. However, this is not a regular graph of y equals x minus 6 or f of x equals x minus 6. When I eliminated this, I forgot something important. this has a restricted domain the same way this or this had a restricted domain. What values of x don't work on this in the domain? Set of all x such that x could not equal, what would make this 0? -6, right? So it turns out even in this case, even though there doesn't appear to have that restricted domain under here, it still does have it. So if I wanted to graph this, this is going to look like the line y equals x minus 6, which is just a, right, it's got a y-intercept of -6, a slope of 1, up 1 over 1, up 1 over 1, except there's going to be a hole in the graph. For the sake of time, I'm just going to use my software here. So this is what, x minus 6 minus 6. There we are. So there's our graph, right? And I might as well. Oh, come on. What's going on here? Line style medium. And what I want to point out, now this is where the computer software is not accurately drawing this, because I know something it don't know. Actually, right there. Yeah, don't know. There we are. So if I graph this, that's what it would look like. However, there's one little thing. I just said x cannot ever equal -6. Now this is not an asymptote, but it turned out there would be an open circle right there, is what this graph would look like. So it looks like a line everywhere, but it is undefined at that location. It's got a hole in the graph. So if I wanted to then also describe, say, perhaps the range, I don't think they asked us to, but the range would be the set of all y such that y cannot equal what? Now this goes from -infinity to positive infinity for its y values, but what y value appears to not exist on this graph? What is the y value of the hole here? -12 is the y value, -6 was the x value. So the domain didn't allow for -6. The range does not allow for -12 in this case. Now to figure out actually what that -12 would have been, if I wanted to do it algebraically, I could have actually just plugged in the -6 here, and -6 minus 6 is -12. And that's how I could have kind of figured that out. So this is a really unique situation for a rational. It occurs anytime your function kind of cancels itself out. It can occur in instance, like you could have a parabola with a hole in it if my numerator was a cubic and my denominator was a linear and it canceled out with one of its factors. You can have some interesting stuff occur. So just be aware of this canceling sort of possibility and when that happens. So thanks for watching, internet friends. Tienen un día el más bien del mundo. Bye-bye. Adios. What's the word? Swag on, chill, cray, cray. There we go. Bye-bye.